So section 4.2, we're going to first look at the fundamental theorem of arithmetic and prime factorization. So what we want to do is develop the skills to be able to solve problems with common multiples and common factors. And one approach that we can use to do this is called prime factorization. Now we looked at composite numbers in the last video, and composite numbers can always be written as a product of prime numbers. They can always be written as a product, but that product can be rewritten as a product of primes. So when we have a number rewritten as a product of prime numbers, it's called prime factorization. Prime factorization is so important in mathematics that it's actually the fundamental theorem of arithmetic. And what it says is that every composite number can be factored into a product of prime numbers that's unique. So you can't get more than one prime factorization. The only thing that might be different is the order in which you write the factors. Okay, so if I factor 30, the prime factorization is going to contain 2, 3, and 5, but not necessarily in that order. And we state that fundamental theorem of arithmetic in this way. Every composite whole number can be expressed as a product of primes in exactly one way, except for the order of the factors. Well, what this allows us to do is a lot of things in mathematics. So once we understand factors, then we can work with fractions and work with polynomials, and we understand multiples. We can do the same thing. And we can do this because this fundamental theorem of arithmetic assures us that there's only one prime factorization. So one method for finding a prime factorization is called increasing primes. So we look at the prime numbers 2, 3, 5, 7, 11, 13, and so forth. And we take the number under consideration and divide by increasing primes if they are divisible. Okay, so 300 is even, so we know we can divide it by 2. So we can write 300 as 2 times 150. But then 150 is even, so we can rewrite this with 2 times 75. Now 75 isn't divisible by 2, but it is divisible by 3. Okay, so you keep up with this process until you have the prime factorization. Okay, so then I have 3 goes into 75, 25. So that gives me this factorization. Here's what it looks like with increasing primes. So we start with 300, and the first prime number we use is 2, and we divide that, and we get 150. Now we see, will 2 go into 150? Yes, it will, so we divide that. Will 2 go into 75? No, but 3 will. So we divide it by 3, we end up with 25. So we've taken all the 2's out. 3 will not go into 25, so we've taken out the 3 we can, but 5 will, and that leaves us with 5. So if I take these numbers, 2, 2, 3, 5, and 5, that's where I get the prime factorization. Another way to find prime factorization is use a factor tree. And so we use a series of steps. We're going to break the number down into smaller and smaller factors until all we have left are prime numbers. So we use branches. It looks like a tree because it branches out. And when the number at the end of a branch is prime, we circle it. So here are some examples. So if I have 30, I can divide 30 up in several different ways, but I'll use 5 and 6. And 5 is prime, so I circle it. Excuse me, I want to get a highlighter here. So 5 is prime, so I circle it. And now 6 not prime, so I keep going. So 6 is 2 times 3. Both of those are prime, so I circle them. So now I have the prime factorization. 5 times 2 times 3, or now that you know the commutative order, commutative property of multiplication, we could write that 2 times 3 times 5. How about 36? Well, I can divide 36 up into several different ways, but I'm going to use 9 and 4. The idea is that it wouldn't matter which way I divided it up. Once I got down to the prime factorization, it's going to be the same. Well, neither 4 nor 9 is prime, so I'm going to divide 4 up into 2 times 2. Those are both prime. And I'm going to take 9 and divide it up into 3 times 3, which are both prime. So I have that 36 is equal to 2 times 2 times 3 times 3. And finally, we look at 126. So if I use the divisibility rules and I add 6, 7, 8, and 9, add the digits together, I get 9, which is divisible by 3. So 3 will go into this 42 times. 3 is prime. So I'm going to take 42 and divide it up into 6 times 7. 7 is prime, so I circle it. And then I continue with 6 as 2 times 3. Those are both prime, so I circle them. So I end up with the prime factorization being 3 times 2 times 3 times 7, or a different order. Here we're going to look at an example where we look at two different factor trees for the same number, and we see that no matter how we decided to divide it up at the beginning, it's going to turn out to be the same thing. So we want to find the prime factorization of 84. Okay, so again, this theorem guarantees we're going to have a unique no matter how we start with our factor tree. Okay, so here's a factor tree where I started with 7 and 12 to be 84, and then finished out the factor tree, and I have 7 times 3 times 2 times 2, which written with exponents in ascending order would be 2 squared times 3 times 7. Okay, 84, here I started out with 2 times 42. But notice that no matter how I started, I end up with the same factorization each time. Now, when we were looking in section 4.1, one of the models we used was a rectangular array of numbers. And we saw that if it was composite, that it would be a pair of numbers that would multiply to get a different number. So we could find all those possible pairs by sketching those rectangular arrays. So let's look at the next example, which we look at the arrays of 24. Okay, now it's not a square number, so each rectangle is going to give us a pair of factors. Okay, so then there are 4 pairs and a total of 8 factors. So I could obtain a list of all the factors just by looking at the rectangular model. Okay, and if I take any one of these and then start a factor tree with them, then I can find out what the prime factorization is. But this factor model of factors, this rectangular array model, will help us when we start to compare two different numbers.